Dear friends, welcome to a second video providing more details on the resistivity method, and as per usual we have about 3 learning goals. One, we will dwell a little bit more on the principle of the 4-point measurement and specific array types that go along with that. And then we will finally allow that the resistivity varies spatially, but for now only along the vertical, and this will then lead to the principle of vertical electrical sounding, and this you will use in your applied exercises, so it's definitely worthwhile to pay attention. Okay, brief reiteration of core results from the previous video. This is a sketch of a 4-point array measurement. We inject a direct current at the electrodes A and B. This will induce a current flow in the subsurface, which we quantify to a certain degree in the previous video, and it will go along with a electrical potential, and we measure the potential drop at the surface with 2 dedicated electrodes located at M and N. And the reason why we do that is that we would like to avoid the effect of this contact resistance RC1 and RC2, which are very relevant at the current electrodes, but much less relevant at the potential electrodes. Okay, and using this principle then allows us to infer the resistivity from the measured potential drop and the induced current using the configuration factor, which accounts for the location of our electrodes at the surface. If the subsurface is completely homogeneous, then this will be the true resistivity. If there are any kind of variabilities, either in the vertical or in the horizontal, then this will correspond to the apparent resistivity, and each time we move our electrodes, we will get a new resistivity, a new apparent resistivity value. Okay, so far so good. So having all these R1s and R2s, R3s and R4s gives us loads of options to position the electrodes at the surface. And there are 2 very famous array types which I suggest you remember. One is the Venner array and the other one is the Schlumberger array. Both of those people have heavily helped in developing the resistivity method in the beginning of the 1900s, I believe. So the Venner array is the simplest possible array because you only need to write down one distance in your logbook. All distances between the electrodes are the same, and correspondingly the configuration factor simplifies significantly. In the Schlumberger array, we have 2 relevant distances, one between M and N, and then another one between A and M or N and B, respectively. Okay, so those 2 array types are very famous. Then there's numerous other array types. For example, we could place one of the current electrodes at infinity. The way this is done, you may learn in the applied exercises, or you can even place one of the potential electrodes and one of the current electrodes towards infinity. Okay, and all of those different array types have different configuration factors. That's totally clear. But what are the advantages of one array type over another? And this is not so simple to answer. However, there's one very obvious effect which I would like you to remember. So if we have current electrodes at the surface, and those electrodes are spaced comparatively far apart, then current flow lines will penetrate comparatively deep into the subsurface. However, if we reduce the distance between electrodes, then the the corresponding flow lines are much shallower. So as a first order metric, you should definitely keep in mind that if the current electrodes are spaced far apart, then you get a deep penetration, but a correspondingly weak signal. If they are close together, you have a much shallower penetration. And in the exercises, we will quantify this concept a little bit more rigorously using the theory from video 1. Okay, and then array types have different sensitivities. So for example, the Schlumberger array is a little bit more sensitive if the resistivity varies in the lateral, and the Venner array is slightly more sensitive if the resistivity varies in the vertical. There are also many other very practical factors why you might prefer one array over another. For example, the feasibility of how you handle those electrodes in the field. Remember, all of those are connected by cables, very long cables. If you need to move those, you need a lot of staff, which again creates a lot of costs. And this also certainly has a large impact on the array type that you choose. Okay, so this is not an arbitrary choice. Each array has advantages, sensitivities in different directions, and also one array might be more practical than another one. And you will learn about this in more detail in the exercises and also in the applied exercises. Okay, finally, let's consider what happens if the resistivity varies spatially. Okay, and for now we assume that everything is horizontally stratified. And in fact, this is an assumption which seems somewhat arbitrary, but it is often the case in geo and environmental sciences that things have been deposited, let's say in a sedimentary setting, which is somewhat horizontally stratified. Okay, so this assumption needs to be taken with care, but it is not totally useless. Okay, and so now obviously the question is, what happens at this boundary? Yeah, so we have now two different bodies. Light gray and dark gray, and they represent two bodies with two different resistivities. Okay, so I'll spare you the mathematical details here, but I pursue a conceptual approach which I believe is understandable enough for such an introduction. If we want to solve the problem at this boundary, we need to apply boundary conditions. Okay, and the key here is again conservation of charges. Yeah, and it follows from that the normal component, so again we are talking about current flow lines which intersect this interface at some angle, okay, and the normal component through here must conserve electrical charges. Yeah, so if the normal component would change, the normal component of the current density flow vector, if that component would change, then this would lead to a continuous accumulation or depletion of charges at this interface, and that isn't really physical. So the normal component should not change. The horizontal component, not a problem. Yeah, this can definitely change with the resistivity contrast. Imagine this being a perfect, nice insulator. Then we would expect most of the current, or essentially all of the current, flowing parallel to that interface. Yeah. So these kind of boundary conditions are quite representative. They also occur if you study, for example, reflection mechanisms of acoustic waves. But it also happens in the resistivity method. Okay, and if you do the analysis more carefully, you can derive such a reflection coefficient. Okay, and this reflection coefficient is between 0 and 1. It will be larger if the resistivity contrast is large, and it will be smaller if the resistivity contrast is small. Okay, and so what does this lead to? So how does it change our flow pattern of the currents? And the key takeaway here is that the current flow patterns are refracted at the boundaries. Okay, because the horizontal component changes, so there is a refraction. And the angle of the refraction depends on the resistivity contrast, okay? And so this leads to a sort of similar flow pattern. It's still a dipole-shaped, but it now contains these refractions at the boundaries, and all of this can be done analytically, but I leave it here conceptually, okay? So takeaway is current flow lines are refracted and also in a sense reflected at horizontal boundaries. Okay, and we can now do this for all layers that you can possibly think of. Okay, we can consider a two-layer problem with one boundary, or we can have 1 million vertical layers. It doesn't really matter. You can solve the differential equations, such as the Laplace equation shown in the previous video, and you can do this essentially analytically. And by you, I don't mean you. Okay, it is a bit complicated, the math. But somebody has done it, and it's not witchcraft, okay? It uses the method of images, and that is something that we would treat, let's say, in a course at a master level, okay? But here is such an analytical solution, okay, which provides the apparent resistivity, rho A, but now we have a fairly complicated integration, and we have to take care of these reflection coefficients, and obviously also the thicknesses of the layers, so how far they are spaced apart does play a role, and then also A is now the distancing between the electrodes, okay? And those J's are Bessel functions, and so on and so on. Way too complicated to derive this solution in this introductory class. But the takeaway is there is a solution, okay? We have a solution for the apparent resistivity, which you can expect if you have a horizontally stratified media. And you can use that solution, okay? So let's just consider an example which might be relevant for your applied exercises. You go to a valley which has some fluvial and other sediments in there, and the way you can imagine this is that you maybe have a topsoil, and below that topsoil there's an unsaturated zone, okay, and then we have an aquifer which is fully saturated, and all of this is underlain by some bedrock material, okay? So this is not an unreasonable assumption for many settings in the geo and environmental sciences, okay? And all those layers are described in a resistivity method with essentially two parameters. A layer has a resistivity, rho, which is material property, and it has a thickness, okay? The thicker, the more important, obviously. There's one exception, the bedrock. It doesn't really matter how thick it is, because in our theory we let this one extend to infinity anyway. So the bedrock is only defined with a resistivity, but all the other layers have resistivities and thicknesses. Okay? So now the principle of vertical sounding goes as follows. We place our electrode in our well-known 4-point geometry, 4-point array, okay, could be Venner, could be Schlumberger, it's not such a difference, okay? And the idea is we start with a given geometry, given distances, which we write down in the logbook. Then we can use the analytical solution in order to predict the apparent resistivity given a certain subsurface model, okay? So if we know the subsurface model, we can predict the apparent resistivity as a function of the electrode spacing at the surface, okay? Forward modeling. We will get to this in more detail in a second. So the principle of vertical electrical sounding is now that you not only do one measurement, okay, this gets you nowhere, but you do many measurements. And the key is that you increase the distance between the A and B electrodes, okay? And by this, you increase the depth of penetration. So you sound deeper and deeper the larger you take the distances, the larger you make the distances between A and B. And for each of the distances, you can calculate the corresponding apparent resistivities. They will always be different for a given subsurface model. Okay? So how would you do these calculations? It's really all prepared for you. Okay? So we provide this a numerical representation of this analytical solution for you on Elias. Okay? It's a forward model that exists in Python and in MATLAB, okay? And you don't at all need to understand all these details here. This is not needed, yeah? But you need to understand that there is an analytical solution. Broadly, you know how it works, so Laplace equation, the conservation of charges, boundary conditions, yeah? This is enough. And then you can use this equation, use this forward model, and you should know what are the input parameters and what are the output parameters. So the input parameters of this forward model will be the subsurface model. So this model needs to know, okay, how thick are the layers and what resistivities are available, okay? And this is stored in this params vector here, okay? And then this forward model also needs to know, okay, where did you place your electrodes? What are the distances between A, M, B, and N? And that's stored in this vector S. So this is the input, okay? And then the output of this model will be one value, that is the apparent resistivity for that specific measurement type, okay? And then I think you know where this is going. You will change S, meaning you will change the geometry. You keep the parameters always fixed. Yeah? The subsurface doesn't change. And then you get a prediction of an apparent resistivity profile that corresponds to a vertical electrical sounding survey. So let's look at some examples, and you will do this yourself in the exercises. Okay? So those kind of plots. Let's familiarize ourselves first with the axis. Let's start over here, okay? What we have on the y-axis is depth, okay, down to 15 meters. That's enough for now. And then on the y-axis, we have the resistivity, units, ohm meters. So far, so good. We know all of this. So this would be a two-layer model with one boundary. And the first layer has a given resistivity, which is 100 ohm meters. And then the deeper, and this layer is 5 meters thick, and then the layer beneath it has another resistivity, 300 ohm meters. Okay, so it's a two-layer model. And now we do our vertical electrical sounding. So it means we have, go to this figure over here, what we have on the x-axis is the distance between the A and B electrodes. We keep M and N in place, so it's a Schlumberger type of array. Yeah? We only move the current electrodes outwards. Okay? So over here are very large distances, 1,000 meters, and over here are very small distances, only a few meters. Okay? So now on the y-axis, we have the predicted apparent resistivity for this subsurface model. Okay? So at small distances, remember, at small distances, we have very shallow penetration of our flow lines. So this means we will mostly see the shallower layer. And a shallower layer has a true resistivity of 100 ohm meters, and our inferred resistivity is about that magnitude. Okay, so that's good. That's what I mean with that the apparent resistivity is somewhat diagnostic of the true resistivity. Okay. Now we start increasing our electrode spacing, and we increase our depth of penetration. That means more and more flow lines will see this deeper layer, which has a higher true resistivity, and so the apparent resistivity averages now over both layers. Okay. So if you only do one measurement and you measure 200 ohm meters, yeah, you could infer, oh, I have a homogeneous half space with 200 ohm meters beneath me. But no, you don't. Really, you have a two-layer case and you average over both. Okay, so the apparent resistivity is diagnostic, but it's not the true resistivity. Okay, and then we go to the other end of the spectrum. We have very, very large distances now between A and B, meaning that most of the currents go through the deepest layer. Okay, there will be a small part still going through the shallower layer, but most of it goes through the deeper layer, and this is why this apparent resistivity profile plateaus. And where does it plateau? Well, it plateaus at the true resistivity of the deepest layer. Okay? So this is a sounding curve of a vertical electrical profile. Those are all predictions. We haven't done any measurements, but if you go to the field and you measure this, okay, then you can at least reasonably infer two end-member models which correspond to those two plateaus, okay, and everything in between is some sort of averaging. Okay, let's look at a different case. Now we kind of turn the whole thing around. We have now a top layer which is, I believe, 7 meters thick. It has 300 ohm meters, and then we have a lower layer which is slightly more conductive. And then we have exactly the same story, but now the sounding curve is essentially inverted. I believe that this is understandable. Okay, next one. Oh, this looks significantly more complicated. So what's going on here? We actually have a three-layer case, meaning two boundaries, okay? So we have a comparatively shallow layer, 1 meter, let's say topsoil, of 100 ohm meters. And then we have a second layer, maybe that's some sand, gravel kind of stuff with a comparatively high resistivity. And then we have a lower resistivity, let's say that's the groundwater, okay? Because there's more water, more mobilized ions I don't know, this could be a reasonable interpretation of this subsurface model, okay? So what is the apparent resistivity profile that goes along with that? Maybe let's start again at this tail end, yeah? Very large distances, 1 kilometer, that is huge. You don't achieve this in the field, yeah? Well, not in your applied exercises, yeah? 1 kilometer, so this is a kind of a very deep penetration. So that essentially should see only the deepest layer, which has a resistivity of, let me see, I think 130 ohm meters. Okay, so this plateau corresponds to 130 ohm meters. That makes total sense, okay? Then let's go at the shallow end, very small distances. We should only see the shallow, so that's about 100 ohm meters. That corresponds again to this end member case, okay? Now, what about this in-between layer, this sandwich layer? True resistivity is 300 ohm meters, but the apparent resistivity is only 190 ohm meters. Why is this the case? Well, for any given electrode spacing, you will always have some averaging of the shallower, more conductive layer and also the deeper layer. Yeah? So you never really have any kind of electrode spacing which would be purely sensitive to this sandwiched layer. Yeah? And therefore, again, apparent resistivity is diagnostic, so there is a lower resistivity layer somehow sandwiched, but the magnitude of this resistivity cannot directly be inferred from the apparent resistivity. Okay? So memorize this. This is diagnostic. You can get some first order interpretations, especially at the tail ends, but everything that's in between is a bit of a gray area because the resistivity method does a lot of vertical averaging. How can you account for that? Well, first, before we account for that, we kind of celebrate now the usefulness of such a forward model, and you will do this in the exercises. Yeah? Such a forward model is hugely beneficial to plan your survey. Okay? So you can go to the literature, you analyze, okay, what is the geo and environmental context that I'm in, which resistivities do I possibly expect, what are the depths that I'm really interested in, okay? So all of this you know ahead of time. Then you can run a forward model such as those, and this will tell you, okay, you know, do I really need to have 1,000 meters spacing? That's a lot of work in the field, or is it enough, you know, to cut it off maybe at 100? There's a huge difference, okay? And huge difference in terms of work in the field, yeah? So this is an example of how you can plan your survey, yeah? If you go further out, this will not help you anything. It just creates work and costs, yeah? So this is an example how you can use a forward model for survey planning, yeah? Quantify your expectations, put some numbers to it. And the forward model, as demonstrated, also allows you to do some, let's say, quick interpretation in the field, yeah? We clearly saw that the short end and the tails are very indicative of the deepest and the shallowest layer. Yeah? Everything in between, gray area. But nevertheless, without a forward model, we wouldn't know that. Okay? But the most important part of this forward model is that it gives you a possibility for a very rigorous interpretation, some sort of model data integration, which we call inversion. Yeah? And this is the same principle that we already encountered in, let's say, the gravity method. Yeah? In the gravity method, we also had a forward model. Given a certain prism in the subsurface, what is the gravity anomaly that I will measure at the surface? Yeah? It's the same problem as given a certain density contrast in the subsurface, given a certain resistivity contrast in the subsurface, what is the response in the apparent resistivity that I will measure? Yeah? So very exact same problem, and so you can apply the same principles. Okay? So we have a forward model. We've seen this slide before. Forward model is now the model for a horizontally stratified media where the resistivity changes with depth. This model requires model parameters, M, which would be the thicknesses and the resistivities of the layers. Okay? Then we apply this model to a certain kind. It's a black box, but we sort of have a good feeling of what's inside this black box, and then we get the predictions. Okay? This is exactly what we did now. The more interesting part, obviously, is that we have observations. So you finally come from a long day of fieldwork. You measured many apparent resistivities, which you collect in this data vector D. And now the question is, which model parameters go along with that? This means I have a set of observation. which subsurface model can explain that? And guess what? The principle of equivalence is also relevant here, and I just show you a snapshot of such an inversion process. Okay, so let me guide you first through the colors. On the right-hand side, we are familiar with this plot. X-axis is distance of AB electrodes, Y-axis is the apparent resistivity. All those blue crosses are our measurements, and they are a little bit noisy and not as idealized as we had it in our first images. Okay, so those crosses are our observations. Okay, now what I did is I went the other way. So I used these observations and found an optimal set of model parameters which would explain those observations, and this is shown with the yellow curve. Okay, so the yellow curve is my best guess of what the subsurface model looks like, and it is so it's a 3-layer case. It has 2 horizontal boundaries. Okay, so is this a good guess or a bad guess? Well, you will never really know. Well, there's methods to find out, but the way I set up this example is that I first went the forward way. So this is called a twin experiment. So I defined an idealized subsurface the same way I did it in the previous slides. Okay, you just assume a certain subsurface model. Then you generate your data. So you make a prediction for this pink curve. Okay, we go over here. This generated the blue crosses, but very idealized. So I added some noise. Okay, this makes these non-idealized crosses, and then I did the inversion. And you see that the yellow curve and the pink curve are not the same. Okay, but the yellow curve explains the observations essentially just as well as the pink curve. Yeah, and this is the principle of equivalence. There may be multiple solutions. Okay, there's multiple explanations for the same set of observations, and the reason is there are trade-offs. Okay, you can have a thinner but higher resistive layer, or a thicker but lower resistive layer, and this could lead to almost the same apparent resistivities measured at the surface. But nevertheless, okay, this inversion provides you with a very rigorous way of inferring a subsurface model from the observations. Okay, the way how inversion works, as stated multiple times, is beyond the scope of this lecture, but you should at least know what it is. And one way you can work with the forward model in your applied exercises is that you apply let's say, a very naive version of the inversion, and that is that you just guess, yeah, have reasonable guesses of subsurface model, make a prediction and compare these predictions with your observations. And if the predictions match the observations, then this is at least a reasonable subsurface model. It might not be the best one, but it's a reasonable one, and this is what we will also train in the exercises. Okay, wow. This brings me to the end of this video. I briefly reiterate, you should by now be very familiar of what a 4-point measurement array is, why we use it, and you should know at least 2 types. Venner and Schlumberger are the ones to remember for your applied exercises. Okay? You are now also able to include a vertical variability of the resistivity. You have a forward model that you can use right out of the box. You don't need excessive programming knowledge at all, and this then enables you to fully and in depth understand the principle of vertical electrical sounding, which you will do in the applied exercises, and you can also do it in the in-class exercises with idealized data sets. Okay? There's still many things that remain to be done. For example, inclusion of lateral variability. Again, we didn't really talk about polarizations. There, we should probably have a better idea of what really steers mechanisms of conductions, like what can we really infer from specific resistivity values, and so on and so on. But again, this is for another day. For now, I thank you for listening, and bye-bye.